Oh, I got close and then I had to sleep at some point. Not enough.
I needed to rush.
Okay, welcome back, everybody. That's going to get in my way a lot, isn't it? So we last time we had, I think, a convincing demonstration of how to control a pendulum. I actually don't consider it solved. Some of us have been talking about this in lab even, but I do think that it's embarrassing that our best solution for the pendulum right now takes the form of a huge complicated lookup table and that we can't kick out, despite all of the powerful tools and optimization that we're going to show you over the course of the class. I don't have anything that can give you a controller that kicks out that's something like sine of x. It would be good, or some very simple write it on a one sheet of paper sort of solution to the pendulum, and I actually swinging up with the torque limit. And I think that's actually a standing issue in the field. We have to address that. But for our model pendulum, if you're willing to have a table lookup, then we've got a pretty good solution coming out. Now the question is, if you want to control more than a pendulum, what do we do? How far does that technique we've already started with take us into more complicated systems? And if it doesn't work exactly, can we make epsilon changes to it? Luckily, we don't have to jump off the deep end. There are a class of systems that are only a little bit more complicated than the pendulum, but that are actually super interesting and cause us, there's a lot of things to think about, and they will actually push our methods in important ways. They are the model underactuated systems. So there's a bunch of them. In fact, there are good books on them. I'll talk about the Acrobat, the cart pole, and a basic quadrotor model. Okay, but just so you've seen them, there are other ones out. There's the Acrobat. I will tell you what it is in a second. There's also, well, let me do it now. So the Acrobat is a 2-link manipulator. Okay, theta 1, theta 2, just like we did in the first class. It's got inertia along its rods instead of just a point mass. Okay, the only thing that makes the Acrobat special is that it's got a torque at the elbow, but nothing at the shoulder. Now the task that we did with the pendulum, swinging up and balancing, that's suddenly somewhat harder if you don't have a shoulder motor, right? And this is where my friend starts asking me, well, if you had more funding, would you put a motor here? In this case, yeah, probably you would. But the reason it's called the Acrobat is you could think of it a bit like an acrobat on a high bar, where you don't really have much torque at your wrist to give, and most of the work you have to do is by swinging moving the inertia of your legs relative to your body, using your strong muscles and your core. Right? So acrobats can do amazing things, and we will try to make this robot do amazing things like swing up and balance upside down, even though it's missing a motor that you would think would be central for balancing. Okay, so that's called the Acrobat. There's another version of it called the Pendubot. Okay, which someone stole the actuator from here and put it here, but then left the elbow off. That's just called the Pendubot, but that's out there too. You can do some of the same games. There's the Furuta Pendulum, which is almost the same. But you take the second link away and put a reaction wheel there. You might have seen that one where you've got a spinning mass on the end of the thing, and you've got an actuator there. So it's almost the same. It's just now your inertia is centered at the joint. Reaction wheel pendulum is another name for these. There's a convey crane system, which is very similar to the cart pole. I just want you to see these and recognize them, and there's a library of them, and then they're mentioned in the notes too that are great fodder for final projects if you want to start playing with them. There's ball and beam tasks where you have a ball riding on a mass or on a plank, and you want to stabilize it to the plank by only moving the plank. Hovercraft is a basic model. The planar VTOL is basically what we're going to call our quadrotor. But there's a bunch of these out there that are sort of they're called the model underactuated systems. And a more sort of classical treatment of underactuated systems would just basically go through this list. There's, for instance, a good book by Fantoni that basically has a chapter on this, a chapter on this, a chapter on this, right down the line. You won't see any optimization in that. That's a book full of mechanical and sort of control, more nonlinear control approaches to those, and we'll bring in a few of those examples of that into our world here, so you can see how they're related. Also, some of the sort of fundamental work on Acrobats and Pendubots and the like was done by Mark Spong. And I'll cite his papers, and even we'll type in his algorithms for balancing, swinging up and balancing at some point. Okay, so there's a library of these systems that you can think about, which are, 2 degrees of freedom, maybe 3 degrees of freedom, but similarly simple, but they're missing an actuator and they're hard to control. Okay, the other, so the cart pole is, some people just call it the inverted pendulum, but since we already had a pendulum, we call it the cart pole, right? So that's just now a point mass here where you can apply a force to the cart and you try to regulate the theta of the rod and also the x position of the cart. Okay, and you don't have a motor here. This is a passive joint. You only get to push the cart or drive the cart. Okay, so the cool thing about these is that they're interesting robots to build. We've built them in lab. One Acrobat. You see it had the like a Acrobat on the high bar and pump up energy. Up. Cool. It's staying up and balancing even though it has no motor at the shoulder. Right? Now, we'll give you lots of different optimization tools for reasoning about that. Some of them show you that you can be very elegant getting to the top in 4 seconds. And in fact, if I had told that to do it 3.5 seconds, it would have probably done it a little faster. But we'll be able to find some solutions that will give very satisfying solutions to this. Some algorithms that give very satisfying solutions to these kind of problems. The cart pole in action, ignore the title, I'll tell you about that algorithm later, but this is the simplest version of the cart pole. And this particular control approach, we tried to demonstrate that it was very robust. and it could swing up and balance at all initial conditions. That problem gets more harder. There's a rail on the end that you have to worry about those. If you're too close to the edge, then suddenly directly. Yeah. How noisy is the status? Yeah, actually, I'm going to talk about that at the end because was there something you saw that made you say that? I'm curious.
I was mostly really impressed by how well these algorithms seem to go to the real robots. Because the simulations rely a lot on knowing exactly where the state is. I imagine if you perturb the state even a little bit, like especially with the pendulum, then you're going to do like slightly the wrong thing and overshoot a lot.
So look closely here. In fact, I have a look closely slide later where I zoom in. Look at the top there, the balancing at the top. We're going to talk about that today. Ideally, in simulation, that thing goes boom and stays. There's a lot of reasons, pretty subtle reasons, and pretty hard to fight reasons why that sort of it does the little dance at the top. That, I would say, so the cart pole turns out to be much easier experimentally than the Acrobat. And you can actually see that in the linearization. There's not that many people have gotten Acrobats to work, actually. I mean, it's not impossible, but it's not that common because it's pretty hard to, it's sort of on the verge of stability. It's on the verge of being able to control it. And we'll understand why. Cool. Any other questions? By the way, so I didn't put drifting cars or on this yet, but this is a good time to think again about what kind of cool systems you have, especially if you have systems that are a few degrees of freedom, but are missing an actuator. So, I mean, there's a bunch of things that are sort of like that you should be spinning in your head about what are these other cool systems that I've seen that look like this that maybe I could apply the same tools. Okay. Let's dig in and see what we can understand from the tools we've already done about how to make these systems work. So, first of all, the equations of motion of these take the standard manipulator form, right? So, okay, for the Acrobat, x is just theta 1 and theta 2, the two angles of the double pendulum, and the input u is my torque at my elbow. Now, I don't actually need to have a saturation on that to make it interesting. It's already hard even if I have unbounded torque, but in practice, if I care about real robots, I'm going to still say that there's some limit to the torque you can apply. For the cart pole, x is the horizontal position of the cart and the angle of the pole. And then u is the force on the cart. And again, I'll put some limits on it. Okay, so what is the B matrix for the Acrobat? It's actually sort of a really hard question if you haven't thought about rigid body mechanics before. The fact that it's a torque between the two links and sort of in the relative frame. How does that relate to the generalized coordinates that we use in the equations? Yeah. that's tempting, but it's actually, it's not. It's because it's a torque against the 2, it turns out to just be 0, 1. If I had written, so if theta 2 was the absolute coordinates relative to the upright, then I would get something like negative 1, 1. Yeah.
Shouldn't you have four coordinates?
Oh, I'm sorry, this is q, not x. And then x is q, q dot in both cases. Thank you. Thank you. Yeah. And b, this b has 2. Correct. Okay, so even simpler than the negative 1, 1. But there's a version of the equations that would look like that. And then this one similarly ends up being a direct force on the cart. Okay, so we have the tools from dynamic programming at our disposal so far. I have a now 4-dimensional state space, you're right. Could I build a mesh over the 4-dimensional state space and use exactly the same tools that I showed on the pendulum?
Sure.
Sure, right? I mean, you would think so. So you can, and in fact, and you'll run value iteration and you'll get a controller out. And then my guess is that you'll run that controller and it'll fail to get to the top, for the Acrobat at least. And then you should proceed by saying, well, what if I added more resolution to my mesh up by the upright? And then you'll run your controller for longer, or your value iteration for longer, because it's suddenly, there's a lot more bins, and it'll almost get to the top, and then still fail. And that's a procedure that you can continue if you're patient, and I think you would succeed. But at some point, it's kind of like, this doesn't feel like the right solution to the problem. There's got to be something better once you get to the top. And it is really a hard balancing problem to stabilize that at the top. Okay, on the cart pole, I think same experience, but you might need more resolution than you expect, but I think this works better, and we've seen that work better. People have accomplished swing up of the Acrobat with value iteration on a mesh. It is possible. I've never had the patience. Okay, so especially at the top, I feel like we need something better. So let's think about the other tool, the other solution we had for DP, which is the linear quadratic regulator, which was the other extreme where we had a closed form solution, but only if the system was linear. This is not linear, but we can make a linear approximation of it at the top. So let's see what that would look like. Right, so just to have written that down. The LQR is the linear quadratic regulator. And this is going to feel like a pretty satisfying solution. Now, the dynamic programming, the value iteration type approaches, conventional wisdom is, it's kind of funny because when we were doing this 15 years ago, conventional wisdom was that you could do it in 5 dimensions, or whatever, and it's exponentially complex in the number of bins or whatever. And now it's 2018 and it's really, computers have gotten really fast, we've got GPUs and stuff, and conventional wisdom is about 5 dimensions still, right? Maybe, some people say 6 now, maybe. But really these things are, if you have to bin the state space in some uniform bin and then do that for every dimension, that grows exponentially, and it's hard to beat exponential complexity.
5 dimensions for X
For X, yeah. So you run out of steam pretty fast. Yeah, unless you can do something clever to reduce the dimensionality, but like you can do some control to simplify things or whatever, but it runs out of steam pretty fast. People do smarter methods and approximate DP and all these other things, but so, especially because I started with, started the whole class by sort of poo-pooing feedback linearization, and I tried to say last time that linearization is different. Looking at the approximate dynamics of the passive original system is very different than trying to impose dynamics through feedback to make it linear. But I want to sort of convince you of that in some way. So let's just look at what it would take, look at the result of linearizing these kind of equations. Okay, so general approach to linearization, if I have some generic nonlinear differential equation, then I'm going to approximate this with a first order Taylor expansion. I'm going to linearize, let's see, about some point, some nominal configuration in state and action. So I can approximate the dynamics around that with the Taylor expansion, which starts off with the function value at the actual point, plus the gradient evaluated at that point. Okay, so this thing, we'll just shorthand that as x dot 0. That's the value this would have taken at x0 there. Plus, this thing is commonly referred to as A, right? And this, unfortunately, is also called B. It is not the same as that B, and so I have to say something like this, and I have to remind myself to say something like that. And I've sweated. I mean, one of the great things about this class, I think, is that it brings topics from lots of different areas into one common notation. And the worst thing about this class is that it's really hard to find a consistent notation that doesn't clobber different disciplines. So that was the one I have never resolved in a satisfying way. So I've got two B's, sorry. Plus B U minus U0. Okay? Now, that's not linear yet. That's a first order Taylor expansion, but this looks, it's like tempting to say it's linear, but you have to change coordinates. So if I say that x bar is x minus x0 and u bar is u minus u0, then x bar dot is now x dot minus x0 dot. And if I bring this to the other side, then I can say x bar dot is ax bar plus b u bar. And that's a linear equation, linear system. So the question is, this Taylor expansion, I mean, it's a tool from calculus, whatever, but we've been talking about dynamics, and we've been trying to live and breathe the vector field of the pendulum, and, are we throwing it all away, or to what extent can this actually capture the dynamics of, let's say, the pendulum? And we can look at it graphically and find out and convince ourselves of how useful this is. So for the pendulum, if I have x equals and u equals tau. I want to linearize around the upright, let's say. I'll do it in vector form. I find I'm sorry if you guys, for those of you that eat and breathe this kind of stuff, but I find that doing this at least once gets all our notation synced up and everything, and it's useful to do. But so if I were to write this second order differential equation in my x dot equals f of x form, then it's a vector differential equation where the first element is just theta dot. And then the second element is theta double dot, which is, I can write as and so that's my vector differential equation. That approximately equals that equation at x0, u0, but without doing any math, I know that I've chosen here a fixed point, so this thing had better work out to be 0. And I'm sure that if you look at this, and you'll see that, yes, sine of I is 0, yes, everything's good. Okay? What's partial f partial x? So my, the standard notation, I almost said my notation, but I think it's most people's notation, right? Is that it's a matrix so that matrix is 0, 1, because this is theta dot, right? This is, what's this with respect to theta is just the ml squared, so it's g over l cos theta of the minus sign. Right? And then the other one is the derivative with respect to theta dot is just b over ml squared. I want that evaluated at my point, right? My partial f partial x, evaluated at the nominal point. So that means evaluated at theta equals pi means cosine of theta equals 1. So this thing gives me 0, 1, negative g over l, b over ml squared. That's my A matrix. and my B matrix with the same work comes out to be 0, 1 over ML squared. Now here is the luxury of working on the board in a class and not trying to make a real robot work. I'm going to just set mass equal to 1, length equal to 1. Okay, I'm going to just drop all the algebra by setting all my constants to 1. I can't quite get myself to set gravity equal to 1, even though that would make my life way better. We'll make that 10, but I did catch a bug though, because if I had used 1, I used 1 once and I got all the way through and had a units wrong and should have been 10.
Should the element in A be G over L positive? Because that implies -1.
Oh yeah, thank you. Cosine of this is -1, yes. Good call. That would change the answer. Okay, so yeah, so let's just m equals 1. You know what, I'm even going to set length equal to 1. I'm going to set b equal to 0. That's even easier. Because we looked a lot at the undamped pendulum. And g equals to 10, which gives me a equals 0, 1. Check my signs here. Like this is 10, positive 10, and then 1. Is that right? 0. Okay, I'll set b to 0. Okay. I hate the fact that the board doesn't erase very well. I wish I could do something about that. But. Can you see that okay?
Sorry, but I'm just wondering.
Yeah.
B over ML squared, is that negative, right?
It is. Good call. Still 0, so that one didn't change my answer, but thank you for fixing that. I did have a negative there too. Okay, and did I get the sign of that one right? Partial this, partial u. Yeah, there's no negative sign on the tau, right? So, okay. So this is a system that we can start understanding the same way we did the phase plots before. We can draw the phase plot of this linear system, right? Theta versus theta dot. Well, we drew the phase plots typically for u equals 0, right? So. For u equals 0, then my dynamics are just x dot equals a of x, right? And we know a lot about how to do that. You just take the eigenvalues of a. So that means the determinant of equals 0, this. So I'm going to take the eigenvalues of a to understand exactly how to plot that, right? If you haven't seen this, it's awesome. If you have, it'll be quick. But so this is just minus lambda 1, 10 minus lambda. So the determinant of that is just lambda squared minus 10 equals 0. So I've got eigenvalues that are plus or minus square root of 10. Okay, and then to find my eigenvectors, I'll stick it back in, say I've got negative square root of 10, 1, 10, negative square root of 10 times v1 has to equal 0, right? So then I get v1 is 1 over square root of 10. And v2, so that's the one that corresponds with lambda 1 being positive, and v2 to be 1 over negative square root of 10. So roughly, 1 1 to 3, 1 to 3. What do those look like? So I've got a line, so V1 on my phase plot. There's some line, slope 3, that goes through the origin, and the other one on my phase plot is negative slope. So this is V1, and this is V2. Okay, so those are just the eigenvectors of the differential equation. And so why do those matter? Because when I'm on that eigenvector, x dot is some a times V1, let's say, then it's just lambda times V1. So when I'm here, I had lambda 1 was positive, so if I'm anywhere on this vector, I'm just shooting out on that vector. Then my derivative lines up right on my vector, and similarly, I'll be out like this, because lambda 1 was positive square root of 10. And if I do the same thing for V2, then if I'm on this vector, I'm shooting down on this vector, I'm shooting down like this. Right, so that tells us almost the whole story. Yeah?
I know your AV is equal to lambda. Right, A is lambda equal to.
Oh, thank you. Jeez. Okay, and so this tells us everything about the phase portrait on the lines. And then the trick, of course, is that as long as your eigenvectors span the space, which they do in this case, then I can write any initial condition x as a linear combination of those two, as, let's say, alpha 1 times v1 plus alpha 2 times v2. So if I have some new position here, I can write it as a combination of this vector and this vector, and then I can figure out what x, maybe let's not call it, let's call it x, I don't know, x42 dot is alpha 1 a v1 plus alpha 2 a v2, which is now just alpha 1 lambda 1 v1 plus alpha 2 lambda 2 v2. So it's a linear combination of the effects from these two vectors, right? So basically, as I come away from here, I'm still doing roughly what this thing is. As I get more of this component, then it'll do more of that. And just following that algebra, you'll see the vector field does this, does this, does this, does this. Is the plot that I wanted to make clear. I've linearized the dynamics of the pendulum around the upright, and I've just drawn the vector field just like we did of the pendulum. This is just a different set of tools for finding out how to draw those arrows. But this is still just the same diagram, which is for every theta, theta dot, I'm drawing the vector, which is the direction that that thing wants to flow when I'm in that state, right? And this is what the picture looks like.
These should be theta bars and x bars and stuff like that, right?
Correct. This is all in the relative coordinates. Thank you. I should be less sloppy about that. Now, the big question is, how good is that? How useful is that? Do you have a...
Yeah. This octane dynamics is valid for a small neighborhood around a given point.
That is the question. That is exactly the question. And I'm going to try to give you a graphical answer. So let's now take that picture and superimpose it on top of the pendulum picture, right? Where does this land on that eyeball that we know so well? Right? This was the eyeball, right? If I were to, because of that change of coordinates, this was around the upright, right? And, I mean, it's going to be spot on here. Like it really does, the homoclinic orbit really does come in exactly like that. So by graphical inspection, I mean, and this is right too, right? This is all good. It's really good. It is really good. Now, okay, it's no good here, right? This one says the vector is going like this, and my linear analysis says it's going like that, right? So if you go too far away, you're in bad shape. But maybe for a pretty long way, it's actually pretty good. And in fact, one of the things we're going to find is one of the fundamental problems that we will try to understand in the class is when you design a controller for the linear system, what is the sort of area in the nonlinear system when it still works? That's a fundamental capability that we'll address to try to compute regions of attraction of controllers that are based on linearizations. Okay, but it's actually, in a pretty big swath of state space, a fairly good reproduction of the dynamics, right? Which is completely different than, when I was talking about, you could just try to erase the dynamics and put in an arbitrary linear system anywhere. That is different. That is, erasing the blackboard and drawing new vectors in. We're not doing that. We're getting the vectors exactly right here and interpolating them with the first order expansion. And the question is just, how fast do those vectors change away from the plane where you did that? How fast, do the higher order terms in the Taylor expansion come in to screw up my linear approximation? And that's a very different question, and I have been surprised and impressed at how far you can go with linear control. Now, okay, one thing you'd like to do is, and this might inspire you to think, okay, well, I'll just linearize here, and then I'll maybe linearize over here, and linearize over here, and linearize. And you can do that, but you open up a much harder problem because, so in this system, this is a linear system that has a fixed point, inside its set. We can call LQR on this and be happy. If you try to take a first order Taylor expansion around a point that is not a fixed point, then that f of x0 didn't disappear. So you have an affine system there instead of a linear system. And you can't do control design of this part of state space by itself, because anything you do is just going to dump into this part of state space. You can't ignore the rest of the world. You have to somehow jointly do an analysis of a piecewise affine approximation. Sure, you can make an approximation of it, but there's something special about linearizing around a fixed point because the dynamics actually come out linear. The Taylor expansion comes out linear, not affine. And you can do the analysis if it's a fixed point like this that you can stabilize. Then you can, thinking about what happens around here and writing a controller that stays around here is a sort of a well-defined problem. If I think about a controller that works around here, but then my controller immediately exits that area, not so good. So this is awesome and magical around fixed points, stabilizable fixed points, but doesn't quite solve the whole problem. Yeah?
Did feedback linearization and just turn some over there into a fixed point?
Maybe. It depends if you have enough torque, right? So like if you're over here, well, okay, you can only have fixed points along the line, first of all. So there is a fundamental thing you can't do up there because you've got velocity. But anywhere around here, if you have enough torque, you could combine those things. Okay, so we have a system, and if you do this for the Acrobat, it's going to look the same, but I can't draw that. But it's roughly the same. I mean, it's two pendula, right? And it's, the equations, there are still sines and cosines, and I just can't draw it. But I think the intuition is roughly the same. That the pictures are going to be nearly as good in the higher dimensional space around the fixed point until you go too far. Okay, so how do I design a controller now? This doesn't do what I want, right? This is not a stable fixed point. The passive system elements here exit away from the fixed point. Can I design a controller locally that stabilizes that fixed point? And for the linear system, I can, using LQR. And it's actually a great exercise to see what coefficients come out and see what changes about the vector, about the eigenvalues and eigenvalues. Okay, but you can really just call well, you can call LQR in MATLAB with my A, B, Q, R, right? Where this is the dynamics where AX goes BU. Okay, and then my cost function that I'm trying to minimize in this case is the long-term infinite horizon X transpose QX plus U transpose RU, that whole thing dt, right? So the controller that comes out is U bar equals negative KX bar, which is actually, if you want to type that in now and run it on your system, that's actually an affine controller. Right? You know that as soon as I have a constant term off here, it's not a linear function. It's an affine function. But if I write this out in the original coordinates, it's actually, I have to add U0 minus K x minus x0. So I've got a U0 minus KX0, or plus KX0, that is a constant term in the controller, plus my, and then, so it's an affine controller. In the original coordinates, a linear controller in the, yeah. So for simple values of Q and R, you can plug that in, see what K comes out to, and see how it changes that, and it's beautiful. You should do it. But I won't do it now because you've already sort of seen it. When we did the value iteration with the quadratic costs of these things, then what did we see come out? We saw a quadratic bowl come out. We also know that the solution here, the cost to go, is JX bar transpose SX bar. And what we saw was the cost to go, well, I'll do the bars here, that's good. It's a quadratic function which it had level sets sort of along these axes, this axis like this, which is the axis at which things sort of kind of flow in, right? It's not exactly the eigenvector of the original system, but it's related to that, okay? And my cost function is about going downhill on this function, right? So this is the level sets of X bar transpose SX. So the farther out I am in a ring here, the more cost I expect to incur, and the trajectories I'll get will do things like that to get there. Now, how long is it going to take this controller to get to the point there from right here? You know, by the absurdity of the question framing, you should know there's an answer that sort of makes sense with that. It does not get here in finite time. It takes exponential, you know, it converges exponentially. A linear system will converge, a stable linear system will converge exponentially. So it doesn't reach there in finite time, right? It'll just get closer and closer and closer at an exponential rate. Okay, so these things will go down and get close there. All right, so that in the vicinity of the upright for the pendulum is certainly a pretty convincing controller, and it is the controller you saw balancing at the top of the Acrobat there. And in fact, it's going to work for a lot of systems. And the machinery turns out to be pretty automatic. The reason for it is well, okay, let me say what systems it works for. So there is a requirement which you have to be controllable, right? So there has to exist, you have to have enough actuators. Like if you're too cheap, then you know, if you didn't put any actuators on your robot, you're not going to be able to run LQR and get a controller out. And so in MATLAB, it'll say A and B are not controllable, right? And so what does controllable mean for nonlinear systems, just to be precise about it? So for x dot equals f of xu, so for a general nonlinear system, so for linear systems, people talk about getting to the origin in finite time. Okay, but for nonlinear systems, getting to the origin isn't enough to say that you can get to any point. So you actually have to say that a nonlinear system is controllable if there's some input. There exists an input in the domain in some finite time. It's an unconstrained U, right? So the controllability does not take, analysis typically does not take into account saturation effects or anything like that. The basic controllability theory says if I can come up with some U with finite duration that can go from any state to any other state in that finite time, then it's controllable. So there has to exist a controller, or there has to exist the ability to command the system to eventually get to the point. If you have that property for a linear system, even just saying that you can get to the origin, it turns out to be sufficient to have this property everywhere, then LQR will succeed for any positive Q and R, and we'll find a way to the origin. Yeah?
Is this a condition on all x, or just for like a particular x?
It's for all x, to say the system is controllable. Now, advanced fact here, if you care, Q, this actually, it makes this a very nice piece of machinery, okay, that there's a lot of different stabilizing controllers that I can generate. I might want some that are to converge really fast, or some that use less energy, or whatever. There's a lot that I can do by just twiddling Q and R. Okay? So, and it's really nice to have a function that you can call that returns almost instantly, that for any positive Q and positive R, and Q can be 0, but R cannot, it's going to return a stabilizing controller. If it's possible, if it's controllable. Now, the advanced fact is that not every stabilizing linear controller can be found by calling LQR with some Q and R. So, if you had some controller out there you're really hoping to get, you might not, searching over Q and R isn't guaranteed to find it. There are other parameterizations that do have that property, which might be better if you're just trying to do a brute force search over controllers, but this is pretty good. I mean, like in practice, everybody uses this because it's how you can make robots work. Okay, so you can turn the crank on any x dot equals f of x u around any fixed point and get out some equations and pop it into LQR, and if it's possible, it'll return a solution. That's awesome. It turns out if you care about the manipulator equations, robots, then you don't even have to do all the work of linearizing all the dynamics, because most of the terms drop away magically, especially at fixed. A lot of it is because you're at a fixed point. Some of it is because of mechanics or the laws of physics or something, but it works out that linearizing mechanical systems is easy. So let's see. If you turn the crank, okay, let me just make it look scary, and then I'll show you that it's easy. Okay, so x dot here, if I write for a general manipulator, is q dot h inverse q BU minus CQ dot minus tau G, plus tau G. This is my manipulator equations, right? Okay, so now I got to take a gradient through in matrix inverse, which is totally doable. It's not that bad. Yuck, though. I mean, first I got to, so for 2 by 2 matrices, yeah, no problem. But go do that for a 6 by 6 matrix or something, and you will be regretting the decision to do that. It turns out you don't have to. That the terms that involve H inverse always have to drop away in the linearization. So magically through cancellation, if you're linearizing around then the whole thing reduces to the only terms that sort of exist are 0, it's a block matrix form here, H inverse partial tau G. Let's see. And then, see, I changed my notation this year, and I keep writing H, and I'm trying to write M. I apologize. If you ever see me write H, yell at me. And I just realized I had to change my sign because I changed my sign on my gravity vector too. Old habits die hard. Okay, that's M inverse, and then negative M inverse C. Okay, so the exact equation of this is in the notes, whatever, you don't have to do it. But the point is, M inverse does appear. M inverse is fine. The gradient of M inverse would be really annoying to have to deal with, and it cancels itself out. Thank God. Well, I mean, you can sort of see it. It's because at a fixed point, it's if you take the partial of this times this plus this times the partial of this, well, this term has to be 0 at a fixed point. So that partial term that you were about to compute doesn't need to be computed. Okay? And this turns out to be really easy. And so in MATLAB, you can only call LQR AB QR. But in Drake, you can call LQR robot, comma QR. And it just does this for you. Yay! I mean, that's like a lot of work, right? Because, not just because of this, but because, I mean, that means you had to be able to auto-diff through your equations of motion of your robot and for arbitrary robots and stuff like that. So, to take gradients of like a full robot equations and do it efficiently and everything. Anyways, so, and no, sorry, it's not LQR. We spell it out. Linear quadratic regulator of robot. You have to tell it the context, which is the x0, right? And then Q and R. You have to tell it where to linearize around. Yeah?
Isn't going to be positive definite?
Yes.
And then the inverse would be the transpose? No, am I just like messing it up?
It is positive definite, but the inverse is not the transpose.
Sure.
That would be awesome. Okay, so let's show you it in action here. Assuming my computer just slept and not died. Oh, that's huge. Sorry. I was like, okay, good. So, I set the upright state to be by theta 1 at pi 0, 0, 0, right? And then I just set the input to be at tau 0. There's a little bit of machinery to just, in the block diagram world, say, okay, you wired the input to 0. Q is 10, 10, 1, 1. It's almost always 10, 10, 1, 1. And there's a reason for that. It's because my My robots are almost always about a meter tall. So the square root, so it's related to the square root of the square root of g over L time constant. So there's a difference in units there, right, between radians and radians per second, which you want to take out, again, with your cost. And the natural conversion of radians to radians per second for a pendulum type thing would be using the characteristic time constant of the pendulum. And if you always divide by 10, you're pretty good. It works for quadrotors too, and they're not meter long. Although Peng's built one that's bigger than that. Okay, so then you call LQR on it, and it kicks out a controller that you can just put into your system. And let's see how it does. Okay, so this is just the pendulum being simulated. At every 10 seconds, it's going to get kicked into an initial condition somewhere near the upright. Okay, and it doesn't jitter or anything, it goes right back up. From pretty big perturbations, right? But not every perturbation. Oh, that's not cool. That's because I didn't put the torque saturations in yet, because that PR didn't land. But they shouldn't have been able to do that. So there's two things. There's two things that are that go bad here, right? So and that are subtle. They're missing here, sort of. Your LQR controller will, if you call it, if you ask it for a control decision far from the upright, it will give you a ridiculous torque. And that may or may not be a good thing. It'll go off to infinity. The other problem is that if you don't wrap your coordinates, if you say, hey, I'm trying to stabilize pi 0, and I'm at 3 pi 0, and I call LQR on my linear controller, it's going to give you a ridiculously big torque that is going to take you away from the fixed point. So you got to do that too. Okay, but otherwise it basically works. And it's going to work for basically all kinds of systems. So there's a planar quadrotor that's there. There's a 3D quadrotor, which the only problem is we're trying to figure out the best way to give you a 3D visualizer through Docker, right? Because Docker can't touch your GPU nicely. And but this is the simple rendering of a planar quadrotor, and it's almost exactly like this, and you just pick the fixed point and you call LQR and it'll stabilize from a huge range of initial conditions. And now quadrotors actually, the reason they're amazing is that basically outrunner motors came online, and you could put a ridiculous amount of thrust out of these little motors, and most quadrotors today are overpowered, and they have a thrust to weight ratio that is way, way, way bigger than 1, and they actually can recover from all kinds of initial conditions like this. And most people use LQR to design those controllers. Okay, and it works in 3D too. If you want to get fancier and you want to handle bigger rotations in 3D, then you'd like to be a little bit more careful about the fact that you're living on a coordinate system that is the rotation matrices in 3D. So you might not linearize the original coordinates. You might try to do a smarter linearization. But if you don't, then it's still going to work for pretty good. It's just about making a better approximation of the vector field farther away. And actually, similarly, in the humanoids, there was a trick, kind of like your question. There was a trick where if you put a controller that basically makes the robot's center of mass stay flat, then the dynamics all start looking, the linearization works better for a bigger region of state space, okay? So there are tricks like that people play, but even if you don't play them, they work pretty well. Okay, so now let's look a little more carefully up here. So this is the zoom in of the question you already asked here. What is the reason for that? And it's actually subtle, but it matters. In some ways, I consider this an extremely satisfying solution, right? So the solution to my Acrobat is contained in four numbers, right? K is just a mapping from a 4-dimensional state to a single action. So it's a row vector with 4 numbers, and that's my controller, and then plus the U0, but that's 0, and so it's basically 4 numbers. I can write that on a piece of paper and be totally happy. I could even truncate the decimals and be pretty, it's like, it's clean, right? But it's missing something. Like, it makes the simulation perfect, and the real robot is bouncing around and everything like that. So yeah.
Didn't you assume that the mass was all like at the end, at the point?
I did not.
Oh, okay.
No. There is a big lead slug at the end of that. Like really, that thing that's wrapped up in, it's wrapped in foam because we didn't want to hit anybody with it. But there's a mass at the end to make it have more inertia there. But it's not because I assumed point mass. It's easy to put the inertias in there. Why would I want a slug on the end of that?
Slow it down a little bit.
It's not quite. We're going to see it. It's going to pop out of the equations exactly next time, but you can guess it now, maybe.
I mean, the energy your Acrobat can acquire by moving it ahead is really not inertia.
Yes, that is the right intuition. Basically, the control authority that you have on this joint at the shoulder depends on the inertial relationship between the first link and the second link. If you have a big, heavy first link and a itty bitty second link, then you're going to go like this all day long and nothing's going to happen, right? Now the problem is you've already got a lot of things hanging off the first link, so it's easy to make the first link heavy. So because the motor, for instance, wants to be at the elbow, we actually put the motor at the shoulder and have a drive shaft going through to try to minimize the mass, the distal mass, put the inertia of the first link as close to the base as we could. Okay, but still, that first link tends to have more stuff on it and gets heavier. The second link can just be hollow tube, but then you get the kind of effect. So you got to put a slug on the end of it, right? Some mass at the end. It's called, the property you seek is called strong inertial coupling, where you have enough inertia in the second link to change the coordinates in the first link. Yeah?
And for this problem, are you linearizing the system around this final pose or around the trajectory starting from initial state?
This is at the final pose, but the way we get there is by linearizing along a trajectory and stabilizing the trajectory.
So if we linearize around the final pose, we can start somewhere around that pose, not everywhere.
Correct. So the swing up part, I haven't told you how to do yet, but you're on to me. And but at the top, it's just vanilla LQR. Okay. So okay, but now you put your engineering hats on here. Why is it jostling at the top? Good. I think that is the biggest reason. So we actually designed. It's a slip drive. Is that what it's called? I just blanked on the name, but it's an unconventional transmission, which is meant to have almost no backlash. But even that amount of backlash still gets us. So it's got a drive, but it's actually got a rubber interface between the torquing shaft and the output shaft, which is designed to have no backlash. But even trying to minimize it, it's still got some backlash. Okay, and in fact, the rubber sort of changes when it gets hot and other sort of annoying things that made us question the decision. But yes, there's some backlash. So what does backlash mean? So if my motor's driving one way and then I suddenly drive the other way, then it takes some effort before I see the result. The standard way to think about that is if I have some gears of my teeth that are pushing this way, and then I change direction, it takes time until I push to the other side of the teeth to see it, okay? So gears have that in a lot, but other transmissions tend to have it too. If you change directions, it takes some time. So as soon as you're at the top, you'd like to be commanding 0, okay? And then you start sliding just a little bit, and it takes some effort to push, and then it kind of kicks yourself back up. And it takes a little bit more effort, kick, you end up going back and forth.
Wait, why can't you put that into your equations of motion?
You can, but it's hard. You can put, because what the effect is a discrete effect, right? So I would have the additional state of the transmission relative to my equations of motion, and I could write that. If it was just a ratio or something, I could definitely write that. But if the dynamics are if this, then go in this direction, the equations are one way, if this, go in the other way, I now have a discontinuity in my vector field. My linearization tools don't go through that, and you need more powerful tools. And I actually would say it's still an open problem. I mean, I think that there's not great satisfying solutions to this problem. Or maybe it's just mechanically, but there's not a satisfying solution.
But if it's close to the point, then should you be able to, that should still be continuous, because at that point your transmission is going in a different direction than the two gears. I'm not a mechanics mech person. They're going in different directions at that point, and you don't have to account for the discontinuity at that point because you're working a really small x.
The point that you were trying to stabilize is exactly at the interface of this, right?
Yeah,
so on the path to it, I agree with you. But as soon as you pass it and try to stabilize it, you're going to get sitting there right between the gears.
Yeah.
And it sucks. And it's, you could also, if you think about the system is passively stable like this, right? In the equations. Okay, but if I ran a wire a little bit much to the left, or if my encoders were offset, so there's encoder discretization errors, but that's super small because we have crazy encoder ticks, okay? But the system is actually not probably passively stable when my encoders read 0, 0, because I have some encoder calibration error, but also because the system's just not perfectly balanced, right? We can sit there and balance it. That's typically how when we're programming it, we'd sit there and go like this, turn it on, and then you'd kind of run away like that. But so it is possible to balance it, but it's not perfectly aligned when it's balanced, just because we're not perfect. Okay. What's another thing that could end up throwing in? So we talked about, I think encoder offsets are probably the second biggest one. Lag. There's two ways you could have lag that matter. One is that you actually have, especially because we use message passing, robot stuff. We send a message and there's some latency between our command getting to the actuator, and so that adds some lag, but that's pretty small. The lag that I worry about more is that I have a state estimator running, which is observing potentially noisy inputs and converging as fairly quickly to the observed output, but that introduces some lag, which is not negligible in the time constant. The goal is to sample your sensors fast enough that the dynamics of your state estimator are much faster than the dynamics of your plant, of your robot, right? And we try to accomplish that, but it's not perfect. And that's a big thing is when those two come closer together. That's why building really small robots is hard. It's one of the reasons why it's hard, is because suddenly the time constants of the mechanics are different. I used to joke that we built big robots because we like to write our controllers in MATLAB, and that was you just needed the controller to be fast enough without a lot of work. Yeah, I stand by it. I think that was a good idea. Okay, so I had one other topic, but maybe I won't open a new thing. Yeah, any other questions about this? Oh, good.
Yeah, it's kind of maybe confirmed it already, but what if, just a couple of questions, what if you maybe made your goal to not exactly center, but a little bit off center, how far you get away? Or even maybe policy-wise, if you said, okay, well, you're to the left of center, or whatever, I'm gonna traject you a little bit to the left and then slowly approach back, right? So maybe changing your goal instead of always constantly having the same.
So it's good. So fundamentally, these things are, I'm seeing if I have any written there, but the LQR and linear control is like an error-driven control, right? So you do nothing until you have some error, and in this case, having some error means you're falling, and then you do something to recover. So a reasonable question is, could you, and that is a fundamental property of having a linear feedback on a system where you'd expect only exponential convergence. There are different control approaches that might try to achieve something in finite time or something like that. I don't think they overcome the backlash issues or these sort of subtle issues, because you know, the problem, I guess I think the most fundamental problem is the place you're trying to stabilize is with 0 torque. You know, and there's just nothing, you know, you want 0 velocity and 0 torque. And when you're there, you should do nothing. That's the right answer, no matter what control design you're doing. And when you start going somewhere else, you got to do something. And so there's an issue. Once you have a, you know, an electric motor in there.
Do you have issues with static friction in the motor and minimum torques?
Yeah, so I lumped that into the backlash, but it's really a combination of backlash and static friction. It really looks the same. Yeah, but especially because it's this torque drive, that's what it's called, torque drive actuator that's sort of like, yeah, in that case, backlash really is for static friction mechanically. Whether it's coming from the actual motor or the transmission, I'm guessing it's more the transmission, but you know, we used, we had enough money to get the Maxon motors, you know, so those are pretty good.
So would you expect this thing to be a lot more stable, trying to balance like this position?
Yeah, I think that's a really good question. So you could stabilize in some other configuration, as long as you, so it's not, you couldn't do this, but if your center of mass is still above the center of mass of the two links has to be somehow above the pivot. And there is a manifold of solutions that you could stabilize. If you picked one of those, you'd be stabilizing with a nut. I bet you're right. I bet you could do that better, because you'd be sitting on one end of the actuator. That'd be fun to try. You can't, I mean, it takes too much torque to do it for, like, because actually some of the control designs, if you forget to put your torque limits in, they'll say, oh yeah, just go like this. And that doesn't work. It takes too much torque. So, it'd be fun to try that. That might help separate out some of those different.
Yeah, but how would you do that if you don't have any motor at the shoulder?
You can do it. So this is a stable fixed, as long as your center of mass of your whole system, right? So that you take the mass of all the links, it exists in summarized in some point, that has to be above the pivot. And that would be another fixed point. So it actually has a whole manifold of fixed points, which is going to be walking along the axis. You know, it's a 0 velocities at all those points. But, yeah.
I don't see how this is
He's saying you lean on you're at least trying to go from, it's from certainly the cogging problem in the sense that you're in both cases, if my command is, you know, 3 instead of 0 at the origin, and if I go this way, I just go down, I apply less torque, then it's possible you're still leaning on the same, right?
So are you saying that you have non-zero torque at the equilibrium?
At the upright equilibrium.
No, it's a time equilibrium.
In this one you would. Because you're holding your elbow at some configuration like this.
Yes.
Okay, cool. Thanks everybody.